This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
I like how you said, yes, you need something that flows, but it's not a fluid. So that led you to sand. That's really a novel idea. And then you're coupling that with the way that you're studying this is not just, all right, we're going to build a building and we're going to stick this damper in it and we're going to shake it on an outdoor shake table, and see how it goes. But you're actually putting it on a cross-laminated timber structure at the Lehigh facility.
Exactly.
So can you describe that study and kind of what you're hoping to learn when you install this in that building at Lehigh?
Yes, absolutely. So when we got this grant, we developed here at SMU a couple of prototype devices. And at that time, this was known in the community. And this idea attracted the interest of Professor James Rickles from Lehigh University, who is a very accomplished scholar in earthquake engineering and structural dynamics. So what we did is we built the prototypes here at SMU. We tested the prototypes. So we designed the dampers, so the sound dampers that they can deliver the force output that was desired for the experiment as the prescribed displacement demands. And we built two of these dampers and we shipped them to Lehigh. And now these two dampers have also been tested as components at Lehigh, and now they are going to be installed in the experimental setup with the cross-laminated timber structure. Before installing it into the larger structural system, we need to test the device alone at the expected force levels or displacement levels that this device will see once installing the structure. And this is called component testing. We test just the device by imposing a prescribed displacement and measuring the force output. And once we know how this device works, then we need to also develop a mathematical model that will characterize the behavior of this device. So then we have information about the behavior of this device, both from experimental tests and from a mathematical model that has matched this experimental tests.
Right. So then you can make larger structures in a numerical and mixed physical model, so hybrid simulation, then you could actually do practically at Lehigh, like simulate a parking garage or something. So how does this hybrid simulation work? We've kind of alluded to it a little bit. It's a mix of some physical specimens and models there, but also this numerical model. Kind of how do these things talk to each other, and how does that work?
So the idea is that if you have a structure that is equipped with various components, you have a mathematical model or a numerical model for the structural system. But then when the structure is being excited numerically by an earthquake, presence of the device is being represented by physical testing. And the force output from the physical testing of the device is being represented in the computer algorithm. So there is a cross-talking between physical testing and numerical simulation.
So that allows you to, kind of like you mentioned, you can change properties without having to rebuild a new damper. You can install multiple of these into a larger virtual structure so that you can see how that interacts. Without having to spend hundreds of thousands of dollars or millions of dollars to build a really large building with hundreds of dampers in it. You can simulate a really large building with hundreds of dampers in it and only build a couple of them.
Exactly.
Yeah, it's going to be really interesting to see how this goes. Lehigh has done this many times with different types of dampers, different types of structures, from steel structures to wood.
Exactly.
What's special about especially testing your damper system at Lehigh that makes this particular hybrid simulation different?
So I think this joint effort with between Professor Nicos and myself is that we try to serve these new ideas of sustainable design. So if I may go back to this pressurized damper that we have developed, this is a very inexpensive energy dissipation device that basically use only steel and sand. So it's a very simple mechanical device to understand and build. It does not pollute. I mean, we don't use any chemicals. It's a very straightforward device that in many ways serves this concept of sustainability, right? We don't have to worry about disposing old oils or anything like this, right? At the same time, cross-laminated timber structures are viewed as promising building technology for not only for low-rise building but also for multi-story buildings. And this is a very viable alternative to concrete and steel structures. So I think my pressurized sand damper, when combined with the cross-laminated timber structure, is a good case study for creating a seismic resistant, sustainable structure.
Yeah, it's really exciting to see these intersections of high technology and advanced concepts like hybrid simulation and sustainability come into play. I mean, I've been around hydraulic systems enough to see like, wow, even the best in the world, you just have oil everywhere that you have to dispose of.
Exactly.
And
exactly.
It's not something that we want to continue if we can help it. And we live out here in Oregon now, and so I've actually seen some of these forests that you mentioned that are managed well by some great timber companies that they harvest a good amount of timber, but they do it in a way that doesn't damage the ecosystem unnecessarily and provides a renewable resource that comes back every 20, 30, 40 years.
Exactly.
And we're seeing that here in the Pacific Northwest, and it's really good to see. Because especially, a lot of these structures that you're designing this system for are for places like Seattle and Portland and cities in Northern California where this timber is coming from. So you're not only reducing the impact of producing concrete itself, but the logistical tail of those type of materials of having to ship them from all over the place. So it's a lot of orders of magnitude of impact.
Absolutely. So all these forests that will be developed to serve this cross-laminated timber technology while waiting for 20 or 30 years for these trees to grow, the fact that all these trees are around will contribute to the reduction of the CO2, right? So it has a multiple beneficial effect by going this way.
Yeah, absolutely. Well, this has been a fascinating conversation, Nicos, and I'm looking forward to seeing where your research goes. For people who are interested in following along, do you have a website or somewhere where people can look at your research as you're going through your testing it?
We have a website here at SMU, so if they go to civil engineering at SMU, they can go under my name, and we have all our publications published on the website, so they can look at them. The majority of our publications are published either in American Society of Civil Engineering journals that it's easy to have access.
Excellent. We'll make sure to stick a link to that in the show notes for this show, so people can grab those links and email you about their thoughts and follow along with your team's research. Nicos, it's been great chatting with you today. Looking forward to seeing how the testing goes out of Lehigh, and thanks so much for the time. I appreciate it.
Thanks for listening to today's episode of Design Safe Radio. Be sure to like and subscribe on whatever platform you happen to be listening to this on. It really helps people find our show. Thanks to our amazing sponsors, the National Science Foundation and the NHERI Network Coordination Office, which is award number 2129782. Big thank you to Marty LaChance, our guest booker and topic researcher extraordinaire, and Raquel Ruiz, who is our video and audio editor. I'm your host and NHERI Facility Scheduling and Operations Coordinator, Dan Zahner. We'll see you in the next episode. Until then, stay resilient.